Hi everyone, and welcome to today's webinar, High Performant IGBT Cooling. Bring your thermal design to the next level with generative design. I'm Gert-Jan, and I'm your host for today. As a quick introduction, since 2018, I'm an AI design engineer at Diabatix, where I'm the first point of contact for our clients to help them with engineering support and getting them started to our platform. I do have a background in mechanical and automotive engineering. In today's webinar, we'll be covering a case study about an IGBT heatsink. In this case, we'll talk about the workflow you need to follow and the main features of the platform. If you have any questions during the webinar, don't hesitate to bring them up in the Q&A section below. I will cover them at the end of the webinar. We'll start the webinar with a short introduction about the case. After that, I will show you how you need to prepare the CAD file for the generative design. Once that is done, I'll demonstrate how to create the case setup in order to start the design process. Before moving to the Q&A, I'll also show you how to post-process the final results. Let's have a look for a summary of the case we'll handle today. We'll start with a short summary on the assembly of the heatsink. As you can see here, the full assembly is consisting out of a few parts. First of all, you have the heatsink, which is covered by a cover plate, and then you have an inlet and an outlet connection. On the inside of the heatsink, there is also a sealing to prevent leakage through the connection with the cover. As you can see here, the cover plate and the heatsink are made out of steel with a conductivity of 80 watt per meter Kelvin, and the inlet and outlet connections are made out of aluminum with a conductivity of 180 watt per meter Kelvin. So this is about the case. Let's have a look what input we need to give for the generative design run. We'll start with an empty geometry, as you can see here. So this is just the heatsink without any structure in it. That's what we call the empty geometry. First step then is to create the fluid region, how it looks like if the design is empty. So if there are no structures in the design, you just have a fluid region like this, and you need to create that in your CAD file as well. Beside that, so if you have the solid region of the empty design and the fluid region of the empty design, we also need to indicate which part of the fluid region may be filled with structures or pins and so on. That's what we call the design space. So there is always in a generative design run a part of the fluid which can be filled by structures. That's basically the space where the generative design has a freedom to place structures. I indicated them all here, so the empty geometry, the fluid region, and the design region, which is part of the fluid region. Now that it's clear how the case looks from a geometrical point of view, we can also have a look to the boundary conditions. As the topic of this webinar is saying, this is about IGBT cooling, and this heatsink is made to cool 3 IGBTs. Each of the IGBTs does have a heat generation of 150 watts, and they are cooled just by regular water. And we apply a mass flow rate at the inlet of 0.01 kilogram per second, and the fluid has a temperature of 20 degrees at the inlet. So we know now everything about the geometry of the case. We know everything about the boundary conditions of the case. Let's have a look then for the constraints of the design. Since it's generative design, we will create a design. So that means that we also need to put some constraints on it. We want to have, for instance, a design at the end which is manufacturable. This case will be manufactured by 3-axis CNC milling, so we also need to enter the parameters of that later on in the system. In this case, we will have a tool size of 2 mm, and the design height is 10 mm. So this corresponds to the depth of the CNC milling. Beside that, we also have a pressure loss constraint, meaning that the maximum pressure loss between in and outlet is set to 165 Pascal, and the goal in this generative design run is to minimize the temperature of the IGBTs. So this is a small summary of how the case looks. Let's have a look now on how we will approach this. First of all, and that's what I will show in this webinar as well, you need to prepare your CAD file. You can do that in your own CAD environment. I will be using Autodesk Inventor for that, since that's our CAD tool, but you can, for instance, also use your CAD tool. As long as you can export a step file from there, it's good. Once the CAD file is prepared, you can make the case setup. That's something that you need to do in the Diabatix platform, so in your browser. Once that is done, we can start the generative design. From there on, you can relax, you can do other things, and you need to wait for the result to be ready. So that's meaning that on the supercomputer, your design is calculating. Once that is done, you get a notification and you can start the post-processing of your case. You can have a look for the results, you can generate some images for internal use, or you can download the step files, for instance. For today's webinar, we'll cover the CAD preparation, the case setup, and the post-processing. Of course, the case need to run longer than the webinar will take place. So I submitted this case already a while ago to make sure that we can also watch the results. So let's start with the first step, the CAD preparation. I will switch now to my CAD environment. As you can see, I have prepared the case already. So you can see the heatsink already now. I've also included the cover, the fluid region, the in and outlet connections, and the design region, as I've shown you already. Of course, I won't go in depth on how to draw this solids in your CAD environment, because that will bring us way too far off the topic of this webinar. And it's of course something different for each type of CAD program. But the main thing that you need to know is you need to come to some solid bodies, and that needs to be a separate body for all your solids, your fluid region, and the design region. So the same regions that I've shown you earlier in the presentation, you need to have them in your CAD program. Beside the solid bodies, you also need to indicate which boundaries you later on need to apply. So for instance, a patch on the inlet, which you can see here, patch on the outlet, which you can see here, and the position of your heat generation. Voila. Once you have this all, so the solid bodies and the surface bodies in your CAD environment, you can start exporting this. You can easily export it as a CAD format. Select step. And if it's the first time that you do that, give it a quick check to make sure that you export with the right protocol. And that should be application protocol 214, which is the default in automotive design. You click OK, save, and your CAD program will export the file as a step file. This step file will later on be uploaded in a platform. So let's switch again to our workflow. We have tackled the CAD preparation, and we can now have a look to how to do the case setup in the Diabatix ColdStream platform. I will switch now to my browser to go to the Diabatix ColdStream platform. As you can see here, it's a fully in-browser software, so meaning that you don't need to install anything, that you don't need to update anything. It's just in the browser that you are typically using that you will work. I'm now showing you the home page of the Diabatix ColdStream platform, and there you can see all the projects that you are executing. I'm working at this moment on a cooling jacket a wafer table, a battery cold plate, and so on. I have several projects, and I summarize or I categorize all simulations and design runs that I do for that project each time in a project to make sure that I have a clear overview of what I'm running. Today we are talking about the IGBT cold plate, so let's enter that project. And you can see that I already started 2 cases. We'll start immediately with adding a new design case. I have done, as I said before, I've done that already a while ago with exactly the same setup. That case has run already in order to make sure that I can show you the result as well today, and that we can go through the post-processing. But let's start with doing the case setup. It's very easy. You simply push the add case button, you give it a name. Let's call it for now temperature minimization of IGBTs, and we select the case type. Here you have the option between a design and a simulation. If you select simulation, you will just do a performance evaluation. So a regular CFD simulation on a case, so you can evaluate the design on or an existing design in terms of temperature, to evaluate pressure loss and so on. You can do that to have some baseline, or you can do, if you have created a design with the Diabatix platform, you can simulate it at other operating points. So you start from an existing design and you evaluate the performance. If you select design, then you will be able to create a design. So then you start from an empty case and you will apply generative design to this case to come to a new design. That's what we will do in this case. So we select design, we add a case, and then we come to, let's say, the main page of that case. Right now there is nothing in there yet. So let's immediately start the setup and upload the step file that we just prepared. And let's populate the case. Now the system will upload the step file that we have created, and he will translate that into all the regions that we defined, all the boundaries that we defined, and so on. So that's what you can see here. Let's turn it a little bit so we see the same geometry as we had in our CAD environment, and that's what I have shown you in the case summary in the beginning of this webinar. On the left hand side, you have your region tree. There you can see all the regions. So that are the 5 regions that we defined in the CAD environment. And if we click on the arrow, you can see which boundaries are applied on that region, or for instance, which sub-region. Let's start with the first region, which is the heatsink. And you can just click on it and then you can start defining. First thing that you need to do is select the region type. You can choose between solid and fluid. In this case, it's a solid. And you can give it a name. I will give it the name heatsink. It's always nice if you give all your solids a clear naming that helps you to do easy post-processing. We don't want to mess up things in post-processing by unclear names, so we always try to give it a clear name. In this case, it's just heatsink, that's clear. We select the material. As I said before, it's steel with a conductivity of 80 watt per meter Kelvin. I select it, and that's all we need to apply. If you want, you can also enable radiation, or you can add a volumetric heat source to this solid. Now that's not the case in this case, so let's uncheck it again, and let's have a look for the boundaries. As you can see, we have the boundaries that we created in the CAD file as well here, and the system automatically detects that it needs to apply that to the heatsink. And then we can start defining them as well. We have different type of boundaries. In the case that you are applying boundaries to a solid, you can choose between a fixed temperature wall where you fix the temperature to a certain value, a heated wall where you fix the heat generation, or an external wall. In this case, it's a heated wall, and let's call it IGBT1, and let's apply 150 watts as we said in the case summary. We do that for the 3 IGBTs. Voila. So now we have indicated for the 3 IGBTs that we approach them with a heated wall, each time with a heat generation of 150 watt. If you think forward already to what the generative design tool needs to create, we said we want to minimize the temperature on all IGBTs, and that's also something that you need to add to these boundaries. So you see the button here, add target. Let's do that. And then you can choose what to optimize for. You have different options going from maximizing temperatures to minimizing temperatures, minimizing temperature spreads if the delta T is important for you, or minimizing variance of the temperature. In this case, it's temperature minimization, and you can apply that to all 3 heated walls. If, for instance, the temperature of one heated wall is more important than the other one, you can play around with the weight. So you can, for instance, bring up the weight to 2 here, meaning that it's, or to, let's say, 0.5, meaning that it's less important than the other ones. Now that's not the case for now, so let's bring it back to 1. So that's it for the first region. Let's have a look for the second region, which is a fluid region. So this type, or in this case, we select fluid as type. We'll give it a name again. And as you remember, the type of fluid is water. Then you have 2 options. Either you can select water with temperature dependent properties, or you can select the properties at a certain temperature. In this case, it's not necessary to evaluate it temperature dependent, so I will choose to fix the parameters on, let's say, 20 degrees. Why is it beneficial to fix the parameters to a certain temperature? The computational resources that you will need to run this case will be lower, since if you want to do that in a temperature dependent way, it's from a computational perspective much more intense. So let's keep it easy now and just select the water at the temperature of 20 degrees. Okay. Then we come to the turbulence model. Here you can select with which turbulence model the equations will be solved. We have a variety of turbulence models available, going from k omega SST to k epsilon. If you're in the laminar range, you can of course also select a laminar model, which is the case in this case study. So let's select laminar. And again, you can apply radiation or buoyancy if necessary. Let's have a look then for the boundaries. So these are then the inlet and outlet region. You can again select which type of boundary you want to apply. You can select pump inlets, fan inlets in the case of an air-cooled case, or you can just fix the flow rate, which we will do in this case study. Let's name it inlet, and the temperature is 20 degrees, which needs to be converted, of course, to Kelvin. And the mass flow rate was 0.01 kilogram per second. And the same can be done for the outlet. There you can as well select, for instance, a fan at the outlet, or just fixed pressure at the outlet. and let's put it to 0. If you think again on the constraints that you want to have on the design, you remember that we wanted to have a maximum pressure loss between inlet and outlet of 165 Pascal. That's not too much, but remember it's a laminar case. And you can apply that on the inlet simply by adding a target and select pressure loss. You can give them the target value, and that's it. Very important to know, let's say that you want to do something else now without finishing the case setup. You can easily go back to the project page and later on continue with this case setup. Everything will be auto-saved, so it's not that you need to save something, or if your computer is running low on the battery and it goes in standby, that you lost everything. Everything is auto-saved, so that you can easily restart your work at a later moment. For now, we will just continue, and you see that there is added a sub-region to the fluid, and that's the region where the optimizer has the freedom, what we called previously already the design region. Let's give it a name as well. And you can select the material that needs to be added. Which is again steel. Then you also need to select the manufacturing, but for that we first need to add the manufacturing parameters that we will be using. To do so, you go to the libraries and you go to the section of material section, or manufacturing settings, excuse me, and you can add a new set of parameters. For instance, CNC milling, 2 millimeters with 10 millimeters depth. And it's along the Z-axis. So that's just the manufacturing name that you will see, and a small description which you can add to help you out. You select the type of manufacturing, which is CNC milling in this case. You can also select, for instance, die casting or 3D printing, sheet metal. Each case you will need to add the relevant parameters. For now it's CNC. As you remember, the tool size was 2 millimeters. And the depth of the milling was 10 millimeters along the Z-axis. And you add the manufacturing method. Okay, so now that that is added, you can go back to the project page. And as I said, you can easily go back to your case setup and continue your work. Okay, so we were adding the parameters to the design region where we needed to select the manufacturing type, which is CNC milling, and then we can add the parameters that we just added. Okay, so we have 2 regions defined. You can see that on the check marks that are appearing here, meaning that we need to define 3 more. Let's hide them. And let's start with this one, which is the inlet connection. It's a solid, we name it inlet connection. And as you remember, it's an aluminum 6061 with a conductivity of 180. We also have the outlet connection, which has the same material. And we have the cover plate, which consists out of steel. Okay, we now have 5 check marks, meaning that we have defined everything that we wanted to define. We can now validate the case, and then the system will check the geometry to see if everything is okay. If that's the case, you get a check mark again, and you can submit the case. Then you can choose which type of case you want to do. You can choose between a detailed design or a conceptual design, and you can choose either you want to have 100 credits for it or 85 credits. What's the difference between these 100 credits and 85 credits? It's a runtime. The credits represent the computational resources that you will apply to this case. If you apply less resources, then you need to calculate longer. If you apply more resources, you will have your result faster. For now, let's go for a detailed design with 100 credits, meaning that we will get a very accurate design in the end, which fulfill all the manufacturing constraints that you set. Okay, case is running now. So which would mean we need to wait for the results. Now we will not do that, of course, during this webinar, but we can immediately jump to the post-processing. So let's have a look again in the workflow where we are. We have done the CAD preparation, and we have uploaded that step file in Diabatix ColdStream. We have applied all the boundary conditions, and we have started the generative design. This will need to run, but we'll have a look already for what you would see in the post-processing. So let's go back to the project page. There you can see that the case that we just submitted is running, and that there is a case finished, and that's exactly the same case that I submitted already a few weeks ago to make sure that I could show you the result today. So if you want to visualize the results, you can just open the case, and then you can see a few things. First of all, you will be entering the case summary. The case summary will give you an overview of the most important parameters, like temperatures on the heatsink, temperature of the IGBTs, the pressure loss, and so on. And you can download the results and the design as a step file. You can also visualize the 3D results. Let's do that for a moment. What will be happening then, the geometry and the result of the design run will be downloaded from the supercomputers and will be loaded into your browser. From here on, you can do then the post-processing, and you can, for instance, show the temperatures on your heatsink, or you can show the pressure loss of your fluid, and more important, you can check how the design looks. From here on, you can also easily take screenshots if you want to enter them in a presentation for your upper management or your colleagues, and so on. Let's have a look how that works. I'll zoom out a little bit to make sure that we can see everything, and I'll hide a few things. Since we first want to have a look for the design, of course. So let's visualize only the design region, as you can see now. So you see the design space that we gave to the optimizer, that he has made the choice in there, either to put solid in there or to put fluid in there. So we filled a part of the fluid with what you can see here as a blue part, with structures to guide the fluid in a certain way. From here on, you can also say, I want to see only the solid, which is like here, or I want to see only the fluid. And now you can also take the screenshots. You can add a transparent background if you want. And download it. Let's say now that we want to visualize the streamlines of the fluid. Can do that. and if you click on it, you can also give them a color, for instance, according to the velocity, and you can rescale it a little bit. Voila. You can also visualize the temperature on your heatsink. Let's do that for a moment. As you can see here, now you can take again a screenshot of the heat generation. So this is a very easy to use post-processing tool in order to make you able to do some very fast post-processing. Let's have a look again to our workflow. We have done the post-processing now, meaning that your case is ready. So you now have a design, and you can see already the engineering time itself is limited to a minimum. You only need to prepare the CAD file and do the case setup. From there on, the computer will create your design, and you will get in a few minutes to your post-processing. So we've come to the end of the webinar, but as I promised, I have left some time to do some Q&A. So let's quickly check in the Q&A section which questions were asked. Okay, so we have a question of Ivan. He's asking if you go to the project page, you can see a picture for every project. How can you set that picture? Let me quickly show that to you, Ivan. So we are talking about this thumbnail here. You easily go into the project and open a case setup. You load the geometry again. You put it into a nice position. You take a screenshot and you set that as a project thumbnail. If you go back to the project page, you see the picture in here, and it's very easy to keep the overview of let's say all your running projects. Okay, let's see which other questions are there. Celine is asking what the difference is between a conceptual design and a detailed design, and that's basically in the name. So a conceptual design or a conceptual test is really testing a few concepts. It's on a low resolution and a much faster optimization to test parameters, to test different materials, test different setups. So it's like you would design something as an engineer at a conceptual level with some sketches and so on. It's at that level. A detailed design is on a very high resolution, with as a goal to come to your end result. So it's on a high resolution. It solves all your manufacturing constraints and so on. So that's the difference between a detailed design and a conceptual design. Okay, then I see we have another question of Alain. He's asking on how he can get access to the platform. That's very easy. Let me share my screen again. If you go to the homepage of Diabatix, which is easily diabatix.com, you can request access. Coming to that page, you need to leave your contact details, and you will get contacted by me or one of my colleagues to get you up to the platform. Then we have also a question of Yekaterina, which I can answer at this page. She's asking if there is some additional documentation on the software, and there is, of course. If you go again to our homepage, which is diabatix.com, you see here an Academy section, and there you have an overview of some interesting blog posts, interesting media following webinars, and you can also watch this webinar as a recording over there. And you can go to the documentation pages, and there per category you have a lot of in-depth explanations about features. For instance, here about user roles. You have a video on what it is doing, how you can change things, and you get feature overviews and explanations. So there is about every feature in the platform, there is some documentation foreseen on our website. And then I think we have room for one more question. And that question is coming from Michel. He's asking what the benefit is of using a technology like generative design in heatsink design. And I think, from my opinion, there are two main benefits of using generative design. It's on the one hand side, the performance. You can reach much better performances with generative design than with conventional design. Sometimes it's up to 20 or 30% performance improvement. So that's one gain. On the other side, you're avoiding the iterative way of making a CAD design, simulating it, analyze the results, redesign it because the results are not good enough. And that whole cycle again, which is very time consuming. So you avoid that, and your engineering time is minimized to a minimum. And actually, the work of your design is done by a computer during the night, during the weekend, when you have a day off, during the holidays. So you minimize the engineering time to a minimum, and that makes that you as engineer can work on other products. So the two main benefits are, one hand side, better performance, on the other side, less engineering time to come to a good design. So that are, for me, the two main benefits. I see that we are running out of time. I know that I didn't have covered all the questions, but I will note them down and I will contact you personally with the answers to the remaining questions. I would like to thank you all for participating in this webinar. I'm looking forward to meet again with you in following webinars. Make sure that you register on our webpage to get invitation for next webinars, and don't forget to request access to the platform. Thank you and see you later.